Okay, today, yeah, yeah, uh, finish Gaussian quadrature. Era. This is a section. Yeah, Gaussian quadrature. Era. Then 7-4. So, what 7-4 is? Yeah, 7-4 present approach. In the present an algorithm. The algorithm allow you to compute an integral as accuracy as you want. Okay, yeah. The error term you can make the error term as small as you want. That algorithm is called Romberg integration. Yeah. Section 4, and then as I remember, I still have section 5 to present. Then after section 5, we finish this book, and then turn to the second book. The second book about numerical linear algebra. Numerical linear algebra, how to efficiently solve large size linear systems, how to efficiently compute eigenvalues and eigenvectors. Okay. Gaussian quadrature era. Yeah. Topic 1. We want to compute this integral. Where W is assumed to be positive. Yeah, AI F XI. Okay, this sum is Gaussian quadrature, and then plus error term. Then what is the error term? The error term, the formula is this. Error. Yeah, 2n plus 2. Take derivative. Then evaluate example sign. Then over 2n plus 2. Yeah. And then integral AB. Q. What is Q? Q squared W. Yeah. Where? Q. Okay. Q. The definition is yeah, x minus x0, x minus x1, x minus xn. That is Q. Q. A special case when AB, this interval, is length less than 1. Okay, yeah, this is a remark in my notes. Yeah, yeah. Okay, case B minus A less than or equal to 1. Because the logs from the interval AB and x also between interval AB. So in the case, right? In this case, Q in absolute value Q, okay, log greater than 1, right? You agree? Log greater than 1. Yeah, because all x between A and B. In this case, the length of the interval less than 1, not greater than 1, then right, then Q less than 1. Okay, in this case, we can drop this, okay, from the error term. Okay. In this case, error term is 2n plus 2. Psi is between A and B, then 2n plus 2 times integral AB omega x. Hey, now, the case, the length of the interval greater than 1, okay, in the case. In the case, B minus A greater than 1, right? How to handle this case? Cut the interval into subintervals. AB. AB, yeah. This is a large interval. Then cut, okay, yeah. T0, T1, T2, T3, Tn minus 1, and then Tn. So that each subinterval, the length less than or equal to 1. Now apply Gaussian quadrature. Yeah. Quadrature AB f x w is equal to summation. Let me see. Integral Ti minus 1 Ti f x. Yeah. What is I? I is 1 to n. Yeah. Gaussian quadrature. Yeah. So here, summation. How about let me change this index J, okay? J, because here I use I. So J. Yeah, J. Summation J from 1 to n. Then Gaussian quadrature, okay? Here. Summation I from 0 to n. AI depends on J, okay? Depends on J. Because over different subintervals. Yeah. X and the coefficient different. So it depends on J. Then F xi also depends on J. Yeah. And then error depends on J. Yeah. Error depends on J. All right, now apply the summation to the two terms J from 1 to n. Yeah. I from 0 to n. AI J F xi J. Now summation J from 1 to n EJ. Now let me estimate the error. Okay, yes, let's estimate the error. All right. Error J from 1 to n E J. Take absolute value. Okay, the size of the error. This is less than or equal to summation 1 to n size J. Yeah. Error formula here. Error. So this is equals to summation J from 1 to n. Absolute value. Okay. Now derivative 2n plus 2. Then Sine j, right? Sine j, what is sine j? Sine j is between tj minus 1 and tj. Yeah, this is sine j. Somehow. And then over 2n plus 2. Yeah. And then integral t j minus 1 tj, right? A q. This q depends on j. Okay, j, yeah, x, then square times dx. Absolute value. Right. I assume each subinterval, the length log greater than 1. So I can drop this, okay? Drop this term. Drop this. So this is less than or equal to summation j from 1 to n. Absolute value on this derivative. Yeah. And then over 2n plus 2. Yeah. Drop, okay. Tj. J, then omega. Okay, now I want to move this vector outside. Okay, I want. Okay, how? How about I let m say be maximum absolute value f to n plus 2. Yeah, this function. And x between a and b. X between a and b. Between a and b, the largest value is n. Okay, so that is less than or equal to summation j 1 to m to n plus 2 factorial, then tj w x dx, right? Good. And now I can move m and this factorial outside. M factorial outside. And then summation j from 1 to n integral tj. Yeah. Tj w x dx. Right. Summation of this integral, actually, this is a m over 2n plus 2. Then integral ab omega. This is the error term. In practice, integral on w usually not big. Say w is 1. Integral on w is b minus a. Yeah. This is it take w is assumed to be positive. So integral from a to b actually is area under the graph of w and between a and b. That is not big usually. Okay. Yeah. How about m? M usually also not big, even though we don't know the function, but usually function f is smooth. Okay. Order 2n plus 2 smooth. So yeah. So between a and b, the maximum number usually not big. Okay. Then there is a denominator 2n plus 2 factorial. This is a very huge number. Say, for example, if I choose n is a, 8, right? 8. Gaussian quadrature. Yeah, the roots x0, x1, x2 to x8. I think 8 is sufficient to have a satisfying error. When n is 8, then 2n plus 2 factorial. This is a 2 times 8, 16 plus 2, 18 factorial. Yeah. This is 18. What is 18 factorial? This is a 6.4024 times 10 to 15. If you choose n is 10, then this is a 20 factorial, maybe a 10 to 30. But this number is in the denominator. Capital N usually not big, and this integral usually not big. So this error actually very small. In practice, n is 8. Good enough for Gaussian quadrature. This is Gaussian quadrature. Then we turn to second topic. Romberg integration. Yeah. Romberg integration. This is a topic 2, section 4. Section 4, Romberg integration. Romberg integration. Yeah, it is an improvement of composite trapezoid rule. But actually, the theory can, I don't think the theory can apply to, other quadrature rules. Say, for example, I don't think, the theory in this section can be applied to, to improve Gaussian quadrature. Yeah. All right. Again, compute this integral. Yeah. AB. Without W. Okay. W, set W to be 1. Now AB, then composite trapezoid rule, cut the interval AB into subintervals, and each subinterval has the same length. Okay, yeah, here, H, same length, H, H. What is H? B minus A over N. Yeah, H. Now apply trapezoid rule over each subinterval. Then we get composite trapezoid rule. Yeah, here. AB. Okay, summation j from 1 to n. T j minus 1 T j. Then f of x. Yeah. Now trapezoid rule here. Okay. Then apply. Then we get again after apply trapezoid rule. Then simplify. Okay. Yeah. Then we get h over 2. F A plus 2 summation j from 1 to n minus 1. Then n A plus j h plus b. Yeah. For the details, you can refer to the section about composite trapezoid rule. Okay. Then what is the error? The error is here. Yeah. Minus 12h b minus a. Then times h squared. Second derivative. Yeah. Yeah. This is a order square. Okay. Order two method. This is order two method. H is arbitrary. Okay. When h is small, that means that you introduce more partition points to the interval AB. Yeah. So h arbitrary. Yeah. This is an arbitrary number. Yeah. So order two method. Now we want to improve this. Okay. Actually, Romberg integration can produce a formula of any order that you want. Say if you want order 100, then you can get a formula from this algorithm. Yeah, x to 100. Yeah, yeah, you can do that. Okay, x to 1000, you can do that. Okay, okay. Now, how? Okay. Let me introduce a notation. Yeah, according to the book. Okay. Yes. Yeah. How about below this part? By T trapezoid. Yeah. Tn. Yeah. Tn. Below this part by Tn. What is H? H is H. H is b minus a over n. Then it can be so that actually not difficult. Okay. Then t to a 2n. Yeah. What is t to n? Replace n by 2 to n. Is equal to 1/2 t to n minus 1. Yeah. To replace the n by 2n minus 1. And then plus hn. What is hn? Yeah, hn is here. Hn. Yeah. Hn is b minus a and then 2n. Yeah. Yeah. Cut the interval AB into 2n, so many subintervals. And then times summation j from 1 to 2n minus 1. F function value a plus 2j minus 1, then times hn. Yeah. This is a relation. Okay, now Romberg algorithm. Okay, now Romberg algorithm. Yeah. Now Romberg algorithm. All right, now quotation. T of 2n, right? Below it by this. Okay, this is a T of 2n. R Romberg. Okay, yeah, capital R. Okay. Yeah, below R and 0. This, okay. Then R0 is T to 0. This is a T1. What is T1? Interval AB. Cut the interval into one interval. N is 1. Yeah. Yeah. N is 1. When n is 1, just Trapezoid rule. Yeah. N is 1. Low partition point. So from A to B. So this is what? Just yeah. Trapezoid rule. Now arrow and 0, n greater than 1, n greater than 0. Then okay, now formula here. Yeah. This is what? This is location. This is arrow and 0. How about this? This is arrow and -1, 0. Okay. So this is 1/2 arrow and -1, 0. Then task here. Hn summation j from 1 to n minus 1. F A task to j minus 1. Hn. Okay, now starting with this definition. Now table, okay, table. Okay. Following is Romberg algorithm. Okay, now compare arrow 0, 0. Yeah, here. Trapezoid rule. Okay. And then compare arrow 1, 0. Yeah, arrow 1, 0. Yeah, set n to 1. This is n is 1, then arrow 0, 0. Then n is 1. Okay. Yeah. Then compare arrow 2, 0. Here, set n to 2. 2, okay. And arrow 3, 0. Okay, arrow m, 0. Okay. Formula is here. Now, arrow 0, 0, 1, 0. You get arrow 1, 1. How to get arrow 1, 1? Formula here. Yeah, formula here. Arrow 1, 1. Arrow n m is equal to arrow n m minus 1 plus 1/4 m minus 1. Arrow n m minus 1 minus arrow n minus 1 m minus 1. How to derive the formula? Yeah, how to divide the formula? Yeah, I can show you. Okay, yeah, I will show you. Okay, how to get the formula? By this formula to get this. Then here to get arrow 2, 1, right? Then get here arrow 3, 1, right? And then here arrow m1. Got the formula. Hey, please note that the second column, this formula doesn't involve any function evaluations, low function evaluations. Number from the first column, then low function evaluation. All function evaluations appear in the first column. Yeah, formula. Yeah. Function evaluation. Yeah. Function evaluation. First column, you need to compute function values. after the first column, then low function evaluation, because this formula doesn't involve any function evaluation. Now, from here, right here, arrow 2, 2, and then this is a arrow 3, 2, yeah, and then arrow M2, okay, arrow M2 formula. Now here, arrow 4, 2, and then this is a arrow arrow 4, 3 actually, because free, arrow 3, 3, and this arrow M3, because column 0, column 1, column 2, column 3, and then so on. So on. Then finally arrow MN. And each arrow in this table is an approximation to the integral. How good the integral? Yeah, here. So good. How good the integral? In the table, okay, I integral AB is RO and M. Yeah, RO and M. Yeah. And then plus some constant only depend on M, doesn't depend on N. Then times HN 2M plus 2. Yeah. What is HN? Yeah, yes. Yeah. This number doesn't depend on N. Doesn't depend on N. If you hold this physics, okay, physics. Yeah. It means that say column 2, yeah, this column, okay, yeah, this is M is physics. So as n approaches infinity, yeah, this go to 0. Yeah, because HN definition, n goes to infinity, this go to 0. So actually, this part, you can make this part as small as you want. Error term. Now, why we have this formula? Why we have this formula? Yeah. Theoretically, yeah, this theory only apply to trapezoid rule. Okay, it doesn't apply to other quadrature rule. Any questions about this error? Okay, about this error. Yeah, yeah. So in detail, yeah, it maybe some is M CM. Now let me plug this in. Okay, this is a B minus A. AB constant is physics. Then 2M. Okay, 2M plus 2. So if n is large, actually this part decrease very fast. Yeah, and also you can apply, apply here. Right? So n times 2m plus 2. When you hold m physics and large, yeah, m is large and physics. So n approaches infinity. Yeah, this part decrease very quickly. really fast. Okay, now the question is how to get this formula. Okay. Okay. In theory, I integral is equal to t to n. Yeah, you need to. I have erased the definition of t to n. Okay. Yeah. Is equal to c to h n squared plus c4 h n to the 4 plus c6 h n 6 and so on. Where c2, c4, c6 don't depend on hn. What is hn over there? B minus a to n. By definition, this is R and 0. Okay, R and 0. Just like Richardson extrapolation. Okay, yeah, I can to increase the accuracy. I can now eliminate hn squared. How? Okay. Okay. Now from this formula. Okay, this formula available only for trapezoid composite trapezoid rule. Right? Yeah. C2, the coefficients, they don't depend on hn. So let me, okay. T 2n plus 1. And then plus hn plus 1 squared plus c4 hn plus 1 4. And then c, yeah, hn plus 1 6 and so on. How hn related to hn plus 1? Yeah. Okay. Now hn plus 1, there is a relation. What is hn? Yeah, here. Do you agree? This is a 2 times hn plus 1 squared, right? You okay? And this is what? This is a 2 hn plus 1 to the 4. This is a 2 hn plus 1 to the 6, right? You okay? You okay? Yeah, you okay? Right? Can you see that? Yeah. hn is b minus a over 2n. Then this is a 2 b minus a 2n plus 1. So this is 2 hn plus 1. Right, now this equation is h t to n plus move the number 2 out. 2 square. 2 square is 4. C2 hn plus 1 square. Then plus 4 plus 16 cn c4 hn plus 1 to the 4. And then 2 to the 6. What is that? 4. 64, right? 2 to the 6. Yeah. 64 C6 hn plus 1 6 and so on. Okay, now let me name this equation 1, equation 2. Yeah. Exactly Richardson extrapolation. Yeah. Hey, now I want to cancel this term, okay, to increase the order. Let me see. 4 times equation 1 minus equation 2. Then again, 4 times, then minus. This is a number 3. Yeah, number 3. Number 3. Then this is a t. 4 times equation 1. So 4 times t to n minus 1 minus t to n. Yeah. Right. 4 times this minus this. Then 4 times this term minus this term disappear. Okay. Now 4 times this minus this. So 4 times this minus this, negative 12 C4 Hn plus 1, 4, and so on. And so on. Now divide the equation by number 3. 4 t to n minus t to n over number 3. And then minus, okay, 4 C4 Hn plus 1, 4. Then minus. Right, now, what is this? Recall the definition of this is a RO n plus 1, right? 0. This is a RO n 0. So this is a so 4 RO n plus 1, 0, minus RO n 0, and then over 3. How about here? Okay, now rename the coefficients. Rename the coefficients. Say, how about D4 Hn plus 1, and then D6 Hn plus 1, 6, and so on, plus. Now, actually, this is what? This is this formula. M is 1. Yeah, this is M is 1. Yes. This is M is 1. Okay, M is 1. What is N? N is N plus 1. Yeah, yeah. This is N plus 1. Yeah. What is the okay? Yeah. Yeah. In this formula, set N plus 1 and N. Let me see if I can get this. Get here. Okay. This is a RO n plus 1, then 0. The m is 1, so 0. So here, pass 1 over 4 to 1 minus 1. Then RO n plus 1. Then m is 1, so 0 minus RO n 0. Yeah. All right, now this is what? This is a RO m plus 1, 0, plus 1/3 RO m plus 1, 0, minus 1/3 RO n 0, right? This is number 3. 1/3, apply 1/3 to the 2 terms. Okay, now, yeah, this term and this term combined, what is that? This is a 4 over 3. R n plus 1, 0, minus 1, 0, R n 0. So this is a 4 R n plus 1, 0, minus R n 0 over 3. So yeah, exactly this. Okay, this is a R n plus 1. Very similar. The D coefficients, they don't depend on H. So cancel this term to get all the 6 formula, all the 6 formula, and so on. So the approach is similar to Richardson's extrapolation. Yeah, this algorithm, you cannot produce an approximation as good as you want. Okay. Theoretically, better than Gaussian coefficient, but practically, I don't know how many people use this algorithm. But I know many people use Gaussian coefficient. Okay. Monday, I still have one section to present. Adaptive integration Monday. So after Monday, then we turn to a second book.